Welcome everyone. In this video we will be talking about algorithms, and in particular we will be taking a look at the binary search algorithm. So the reason that I'm making this video and the reason that I made this app is because this is a learning opportunity for myself. I'm currently in the process of learning algorithms or skilling up in that area, and I figured it would be a good way to also bring Flutter into the mix, as Flutter is such a good UI toolkit that I can use Flutter to basically visualize the algorithms as they are being executed, if that makes sense. So instead of just doing the algorithm, create some way you can visualize the algorithm running. This will be more clear once I actually do an example of binary search. But yeah, as I said, the reason that I'm doing this is because I'm currently also learning these algorithms, and the platform that I'm using to do that is called AlgoExpert, and it is absolutely amazing. AlgoExpert is basically a platform that prepares you for the interview environment. As you can see, they have 77 questions at the time of this recording, and these are typical questions that you will get in a coding interview. I'm not currently authenticated, but I've already completed all of the easy ones. I started with the medium ones, and while I was doing one of these questions, I had the idea to create an app in Flutter to visualize the algorithm, and that gave me the idea to basically create it for all of these algorithms, or at least for the algorithms that I can figure out a way to visually represent. But yeah, AlgoExpert is fantastic. For each of these questions, you also get a companion video to basically explain the algorithm and go over the space and time complexity. And it also supports multiple languages. And honestly, what I like the most is the fact that they give you a variety of different solutions. For example, one solution may be more optimized than another. So yeah, if you are preparing for coding interviews, definitely check out AlgoExpert. I've recently also became an affiliate for them. You can use the promo code FUNWITH for a 15% discount. I will leave a link in the description. That's it, let's go on over to the Flutter app. At the end of the video, for those of you that are interested, I will go over the code. And for now, let's just actually demonstrate the app. As you can see, we have linear search over here. So as you may expect, if you enter a value, for example, 38, it will linearly search through all of these until it gets to the value of 38. And as you can see, there are some fancy animation going on. Cool, it says value found at position 9. Nothing too fancy, as you would expect. It's just a linear search. Let's explore the binary search, the reason I made this application. So instead of me explaining what binary search is, let's just run the app and visualize it. So we're going to search for 11. As you can see, it goes to 38, it cancels out all of these, and then it just magically goes to 11. So if you know how the binary search algorithm works, this might make complete sense to you. But if you're not familiar, what is happening is we are taking this array and we are dividing it in two. So we are essentially finding the middle point. And here the middle point would be between 38 and 39. We're going to 38. And then we're saying, is this value bigger than 38 or smaller than 38? And 11 is smaller than 38, so we're canceling out everything to the right side. So as you may have noticed, a binary search algorithm would need to be applied on an array that is already sorted. If this array was not sorted, then it would not work. So going back to what I said, we have discarded the right side of 38. So now we know that the value should be somewhere between 0 and 35. So what we do is we divide this again by 2, which is the middle point over here, which is 11. And we compare 11 to the value that we're looking for. And 11 is 11. So cool, we found it. Let's do 4 as an example. Again, we go to 38, we cancel out. 11, we cancel out. 1, we cancel out. And 4, we found it. So as you can see, what the visualizer does, it basically discards all of the values that the algorithm knows the value can't be in. All of these red ones that are crossed out, the algorithm will never look at those because it knows it can't find the value in those nodes because the value was either bigger than or smaller than those respective nodes. The blue ones were values that were actually searched, and the green one means that it was found. So let's look for a value that doesn't exist, for example, 70. And now you can see it discarded the first half because 70 is bigger than 38, and then it just continues to do that until finally it has run through all of the available nodes, it couldn't find the value and the algorithm quits. And that is basically that for now. As I said, I want to do more algorithms. I've started the bubble sort one. However, I'm still contemplating the best way to move these individual widgets as they are sorted. But that is for the next video. For now, if you are interested, keep watching. I will explain the actual code. Or if you prefer, you can just jump on over to GitHub. I will leave a link in the description to the source code. So let's look at the actual algorithm in code. The linear search is straightforward. We are just doing a loop, and then for each value in that array, we are evaluating if it's equal to the target. If it is, we are returning the position, and if it's not, we return -1. -1 meaning that it is not found. So as you can see, I've marked over here that this function is not used within the application. I'm just creating this as a convenience method, or basically just to illustrate what this would look like if it was just a pure function, if it wasn't doing any fancy animation. Later on, I will jump on to the function or the method that I use that does the animation as well. And if we go to the binary search one, you can see that it is a bit more complicated. We have two methods, a binary search and a binary search helper. So this is the one that you would be calling from your application. You provided a list of integers and a target value, and then it calls the helper. And here we give it a left and a right value. The left value will be equal to 0, and the right will be equal to the length -1. So to visualize this, let's search for 11 again. And in this instance, the beginning of the search, the left value would be 0, so index 0, and the right value will be 74, meaning the length -1. So we're saying length -1 because the index starts at 0, because this is a list. Then comparing 11 to 38, we found that 11 is smaller than 38, so we know that 11 has to be on the left side of 38, so we discard everything. And then we give it a left value of 0, which doesn't change, it's the same as the previous function call, and a right value of 35. So this logic happens in this while loop. So this while loop will happen as long as the left value is smaller or equal to the right one. If the left one is ever bigger than the right one, then we know that the value was not found. And we determine the value of the left and the right node by either decreasing the right one or increasing the left one, depending on if the target is smaller than the potential match. And the potential match is only the middle value of the list. If you want a better explanation, definitely check out AlgoExpert. They do a fantastic job running through all of the algorithms and explaining them in a lot of detail. But as I said, I do not actually use these algorithms. They are only here to explain the code or the code behind these algorithms. Let's look at the actual UI. I'm using the provider package for my state management, and I will get into more detail in a moment. For now, let's just actually look at the UI. We head on over to the home page. You can see that the home page is just a page view, and this page view just builds the 3 pages. So linear search page, binary search page, and then I'm using a package called dots indicator to highlight or display the page that we're on. Okay, next let's head on over to the linear search page, and the linear search page is mostly just this column. I will get to the stack now, and as you can see, we have a title, then just some spacing. Then we have an expanded search visualizer, which is this, then a search message, and a size box, and another search. So this will be the value in the search. And as you can see, for all of these widgets, I give it a specific type. And the type that I give it is that of linear search provider. And the reason that I'm doing that is because the linear search page and the binary search page are very similar. The only difference is that they are using different providers. So the linear search page obviously uses the linear search provider, and the binary search page uses the binary search provider. Aside from that, they are identical. I could have actually abstracted this even more and given the type opacity type over here and then add less code, but for now, I feel like it's abstracted enough. I will go into detail how I'm achieving this in a little bit. But sorry for the rambling. Let's go back to linear search and linear search over here. Let's look at the search widget. So we go into the search widget. You can see that we are requiring a type type T, which extends a search provider. And a search provider is the base provider class that I created. Let me show you. If we go to our providers folder and go to search and head on over to search provider, you can see that the search provider extends change notifier and that this is an abstract class. So this class gets extended by our linear search provider and our binary search provider. So let's open linear search provider, and you can see it extends search provider and it overrides the search method, calls the super on the search, and then has a private method called start search. And this is exactly the same as the linear search algorithm that I showed you here. The only difference is that we are doing some awaits to create the pause effect, and then doing some additional logic to simulate the animations or to make the changes in our objects that trigger the animations. The same for binary search provider. The only difference is it's slightly more complicated, as you can imagine. So let's go back to search.dart and go through it step by step. As you can see, we have this method called search. And what this does, it passes the value in the edit controller or the text editing controller. So this edit box over here. And then it takes that value, and using provider, we call type T. And you may remember that we pass in a type of linear search provider over here. So this is the same as saying, instead of saying type T, we can just say linear search provider. The only reason that I'm not doing that is because I'm reusing this widget. I'm using it for the linear search provider and I'm using it for the binary search provider. So let's change that back to a type of T. And as you see, it extends search provider, which is the base class for our providers. And then on that provided value, we call the search method. And this search method over here, or the search function, is called within our raised button. So when this is pressed, we call this function over here. And as you can see, we are also controlling whether the search box is active. So for example, if we start a search, then the search box is no longer active. And that is controlled by a consumer, or not the consumer, but the value retrieved from the consumer. So this consumer gets the value from the provider, and then it takes the provided value and see if the is searching field is currently active, if it is true, and it is only true if the algorithm is running. And based on that, we are either returning null or we're returning our function over here. And that is that. If we head on over to main, here you can see that we inject the linear search provider and we're using multi-providers. So we are doing a linear search provider, binary search, and a bubble sort. And these are a change notifier provider. So once they change, all of the widgets that are subscribed to it will be notified. One important thing to note is that over here, we are saying listen false, meaning that this won't listen to changes, as all we want to do is just call the method on the provider. Okay, so with that out of the way, let's go back to linear search. And now we have a search message. So if we jump on over to search message, you can see that we also give it a type of linear search. And this is exactly the same, or the same logic, I would say. We have a consumer, we get the provider, and then based on the provider that we get, we have all of the information that we need. We have the position. I will go into detail for the provider later. But yeah, the provider exposes all of the values that we need for the UI changes. And based on the value that we get back, for example, if it is -2, then it is searching. If it's -1, it's value not found. And if it's something else, then it means that the value has been found. Okay, next up, we are going to go back to our linear search page. And this time we will look at the search visualizer. So this is where it gets a bit more complex or a bit more interesting. Here we have a consumer again, type T, and we have a wrap. And what a wrap does, it's the same as a row, but once there is no more space, then it will wrap to the next row. So no matter how many child widgets we give it or children we give it, it will always just wrap to a new column or row. So it will just continue to basically fill the screen as necessary. And based on the value that we get in the consumer, we have an iterator. So we have a for loop that goes over the provider, goes over the numbers, and then we call search widgets. And search widget is a widget that is basically just these numbers, but with fancier UI. And how we achieve the animation is by using an implicit animation. So we have an animated container. And depending on the states of each of these widgets, I'll go into these states in a moment. Each of these numbers are of type search model. So if we go to the search model, you will see that it has a value, and the value is essentially the 0, the 1, or the 4. Then we have a state, and the state can be open, discarded, searched, or found. And then we are generating a key. So for the linear search, we aren't using the key, and I will get into the key in a moment. For now, we don't need to know what this does. And as you can see, the search model has a number of different functions or methods that you can call, and I will get into them as well in a moment. Now, all we need to know is that this search model has a number of values that we are interested in, and one of that values is the state. So basically, what state the node is in. Has it been searched? Is it open? Is the value found in that node? So let's head on back. And then you can see that we have this number, and on this number we are checking to see if the state is search. The state is search. All we do is increase the font size. It's found, we increase the font size. If it's searched, we take it back to the initial value of 20. And that is how we achieve the animation to get the text size animating. And the text size is actually not happening with the animated container. That is happening with this animated default text style, which is another implicit animation that Flutter provides by default. And to use these two, all you need to do is provide a duration and an optional curve property. And the curve is just the interpolation for the animation to happen. So for example, does it happen in a linear way, or does it happen in some other fashion to give you a different animation effect? And then also, depending on the states, we can set that the decoration for the text should have a line through or none. So that is what the lines through the red nodes or the discarded nodes are. And then on the animated container, the actual animation or thing that we are animating is the color. And as you can see, we have a box decoration. And on the animated container, the thing that we are animating is the box decoration. So as you can see, depending on the state, we either have a border value of null, or we give it a border that's green, which is this border you see over here. And then another thing is that we are animating the color. So on this number node, you can see that we also have a color property. And in our search provider, our linear search provider, we set the states of the color, or we set the value of the color to different values depending on the search state. So that is most of the UI. Aside from the, sorry, this is the wrong class, aside from the search indicator. And the search indicator is this box that is following the animation or the progress of the linear search. And that was a bit more complicated to do, and I will get to that in a moment. Now let's actually go to our provider class. So if we go to linear search provider, you can see that this extends search provider. And the search provider is where we have most of our methods. And again, the reason that we are doing this is because the linear search provider and the binary search provider are very similar. They do the exact same thing. It's just a slight variation on the algorithm. So let's see what is happening under the hood for the linear search provider. The search method is exposed, and we are calling this when we hit the search button. So then we call super.search. And what super.search does, it calls the reset function and sets is searching to true. So by default, when we create this class and we set the position to -2, meaning no search is happening, or meaning that the search could be in progress, and then we are setting is searching to false. And as you can see that the search method is marked with the meta flag to say must call super. If we override the search method, we must call super as well. So let's look at reset. Reset does what you think it does. It sets the value back to false, set the position back to -2, and then it does a for loop on all of these numbers and calls the reset method on each of those. And if we look at reset, what this does, it sets the state to open, meaning nothing is happening. And the color, back to black, sorry. And that is that. So let's hit back and go to our linear search provider. And then after we have called super.search, we call start search. And start search gets a target number. And then we just do a for loop over all of the numbers. We get the numbers from the super class. And then we call potential node. So for each number we want to see, is this a potential match, yes or no? So we call potential node. And as you can see, potential node takes the numbers value and calls dot potential on that. So numbers is this list over here. It takes the index at that numbers and calls potential on it. And what potential does, it just sets the state to search and the color to blue. So at this point, I hope you get a sense of the layout. I'm just going to go and tell you what each of these does. Discard, as you can imagine, it discards it. And found it. And for each of these, we set the relevant state and we set the color to the relevant color. Same for search. However, for search, we do not change the color because it will just remain blue. So let's head back. And then after we call potential node, we call await. And this wait is a utils function. And all that does, it just sleeps for 1 second. It just returns a future delayed of 1 second. And then we see if this number is equal to the target value. If it is, we call found node. And found node will set it to be green and will increase the size. And we'll set the state to found. And then we return, we are done. Else we call discard node, meaning we set this to red and we change the size back and we set the state to discarded. And if the entire for loop is finished, we call node not found, which will result in the provider returning -1, which will result in the provider setting the position to -1. And as you can see, for each one of these, we call notify listeners. And that is what triggers the UI updates. And if it is equal to -1, then this will say value not found. And that is that. So let's head on over to the binary search. This is very similar to the linear search in practice. However, the algorithm is obviously different. So the exact same thing, we call search, we call super.search, which is the exact same as linear search. And then we call start binary search. And over here, move this out of the way. And then over here, you remember when we went over the algorithm, we had a list, we had a target. Then we have a helper method as well. And here we have to pass in a left and a right value. So let's quickly go over the algorithm as we go through the code. We see if the left value is smaller than the right. So in the beginning, we will do a search that goes from left to right, and then from left to right, and then we found the value in the middle. So this is what's happening. We're getting the middle value. We call potential node to say that it could potentially be middle, which sets the color to blue and increases the size. Then we call await just for some animation pause, as the animation will require some time. If we don't actually call await, then the updates will be so fast that the animation won't trigger. As an example, if we take out all of these awaits and do a restart, go to binary search and search for 11, it will just immediately do the final transition. So that is why we have these waits, just to create the animation effect that we want. So after calling await, we get the potential match. And we see if the target is equal to the potential match, then we are finished. We return the found node, this middle value, the index, and we call found node, which will set it to be equal to green and set the state to be equal to found. Next, we test to see if the target is smaller than the potential match. For example, if we're looking for 11 and our first target is 38, we see that the target 11 is smaller than the potential match, which is 38. And then what we can do is we can discard everything to the right. So we take the middle index plus 1, and then we take the right index, which is over here, 74, and we call discard nodes. So there are two methods, discard node and discard nodes. And this one just discards multiple nodes. So we go from the left to the right, and for each one of those individual numbers, we call the discard function. And that just sets the state and sets the color to red. And then we call await, and then we make the right value slightly smaller. So then we say that the right value will be 35 now, and the left will stay at the current position, which is 0, meaning the next iteration of binary search helper, or this next while loop, we will look at the middle value over here, which is the middle value between 0 and 38. And then the final piece of logic, if it's not smaller than the potential match, or if the target is not smaller, it must be bigger than, because we've already tested the scenario where the target is equal to the potential match. If the target is bigger than, then this else will trigger. And then we know that we want to discard the left-hand side. So if we were looking for 44, for example, then we know that it must be somewhere between this value and this value. So we can discard the left side, and that will be the left value, and middle -1. So we discard everything to the left over here. And then we just increase the left pointer from middle to middle +1. So now the left pointer would be here, right pointer would be over here. And then we do the exact same. We get the middle value, and then this entire process happens again. And then at the end of this loop, we call search node, just to say that this node has been searched and it's finished, and meaning it's not currently being searched, it is not discarded as it was searched. And then last we call search node, and that just sets the node to a value of searched, or it sets the state to be searched. And all that does, it just makes the size to go back to its initial value, and it keeps the color to be blue, meaning that we did look at it, it's not discarded as we looked at it, but it's definitely not the value that we were looking for. And then last but not least, we call not found, meaning we looked at all of the values, left is now bigger than right, the left pointer has gotten to a point where the right one and has overlapped it, and we say nothing was found. And for node.found, you can see we're setting the position to be -1, and we are notifying listeners. You might have noticed that we are returning -1 and an int of future. This is actually not even necessary. I'm just doing that because that's how I initially did it, and honestly, I just realized that technically this doesn't need to be here, but I'm going to keep it. There might be a reason why. Maybe I'll need it in the future. No point in removing it now, I guess. Okay, and now for the last bit of magic, and that is this little indicator over here that follows the animation as it moves. So if we go to our linear search page, or let's say it on binary search, you can see that this entire column is wrapped in a stack, and at the bottom, the last widget in that stack is the search indicator. And again, we give it the type that we want, and or the provider type that we wanted to emulate. And then let's go into search indicator. This is by far the most complex animation, or the most complex widget in this entire application. And that is because we need some way to get access to the position of each of these widgets in this wrap over here. And how I did that is by using global keys. So if we head on down here to the source code, we have our regular old consumer, and we get the search provider. And then for each of those, we iterate over the numbers. And then we check to see if the state is currently in search. So if the state is currently set to search, it means that, for example, this is search, 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 and found. These are searched, meaning they are no longer in search, they are the past tense, searched. So at any given time, there is only one node in the search state. And we find the first one that is in that state, and then we call break. And before we call break, we set the position, and the position is a offset value, as you can see over here. And this offset value we get by calling getIndicatorOffset. And what this does is we pass in the search model, which is essentially the number. And you may remember that this search model has a key attribute as well. And this is a global key. So let's jump into that. And you can see when we create the search model in the constructor, we also initialize a key value of global key. And we use this number.key to get the current context and then find the render object. And then we can convert this to a render box. And a render box has a local to global method. And we give in offset.0. And honestly, I'm not even sure why. I think this is just an offset value. But either way, we get the global coordinates of this render box. And that will give us the screen position. So as an example, while we iterate over all of these numbers, we start at 0 and we get the position of 0 by calling getIndicatorOffset. And then we get the screen position of 0. And then we use that screen position to animate the position of this container over here. That was a lot of words. So this container is this search box over here. And we pass in that as a child to our consumer. And the reason the child is at the bottom here is because a consumer can have a child. So this is a slight optimization, meaning that the child won't be rebuilt every time this builder fires. Instead, we create the child once and then reuse that every time this builder fires. This is only really useful if it's a complex widget, but might as well put it as a child. And then we have an implicitly animated widget called animated positioned. And this animated positioned will change its position by animating to a new value. So we give it a duration of 400 milliseconds. So every time this position attribute or this position value changes, so this offset, the position will get animated. The container will go to a new position by animating using this curve that we provide. And then the last bit of logic is we are only making this visible if the searching is actually happening. As you can see, the indicator vanishes when it is no longer searching, and it only appears once the searching has begun. And that is controlled by this true or false property that is within the visibility widget. So important to note that this positions will only work within a stack. So if we go to our binary search, you might remember that this is within a stack. And that is how we animate this container over here. And that is that for this video. It was a lot. I'm not sure if anyone is still there. If you are, let me know in the comments. I would like to know if someone actually finished the whole video. And if you did finish the video, drop me a message, tell me what you liked, tell me what you didn't like, and I will maybe send you a free link to my upcoming course, a course on animation. I glanced over a lot of the implicitly animated widgets that I used in this video, and implicit animated widgets are only one small factor of animation in Flutter. And I've recently been working on a new course that goes over everything animation wise. So if that is something you are interested in and you are that dedicated enough to actually watch this entire video, and if you enjoy me rambling, then yeah, drop me a message. I will send you a free link once or if the course is ever finally available. Anyway, cheers, catch you in the next video.